Firstly, I would like to thank the organizer to organize this nice meeting and in this beautiful city. And also thanks the meeting provide us this opportunity to provide you this, to show you a little bit on the current progresses of this first Chinese X-ray astronomy satellite. So this talk is presented by me, but on behalf of this PI, is Professor Zhang Shuangnan, and also this talk is prepared by him on behalf of the entire team. And the outline of this talk is that I will show you firstly a little bit on the mission and the payload, and afterward is performed observations and preliminary result, and finally is a summary. For the mission and the payload, the full name of this HXMT is a hard X-ray modulation telescope. It was actually China's first X-ray satellite. It was selected in 2011 and has a total weight of more than 2,000 kilograms, and it has a circular orbit of 550 kilometers with inclination angle of 43 degrees. And has a pointed scanning and GRB mode, and I will come back to this issue again later on again. And it has a design lifetime of at least 4 years or even longer. It was launched in last year and also dubbed at Insight. I will show you why in the next slide. For the history of this Insight-HXMT, it has to be traced back to last century with a series of balloon flights to test the prototype of the satellite. It was firstly proposed as a satellite in 1994, but finally it was founded in 2011 by the first PI of this mission is Professor Li Tipei, showing in this figure. And Insight, its name was taken just in honor of this Chinese scientist, He Zehui. And one of her first name, Hui, means insight. And was launched in last year in China, in Jiuquan, showing it here. And for the core sciences of this mission is that we want to use it to perform the galactic plane survey, to hunt for the weak and relative short transient source in rather wide energy band. And also we want to use it to perform the pointed observations for observing the bright sources and also this XRB in their all burst in high statistics and high cadence. Of course, you know the multi-wavelength observations joined with other telescope and also GRB, GWEM counterpart and FRB are also our favorite core sciences. A little bit on the payload is that as shown in here, located at the central part of this platform is our major telescope, so-called HE. It's kind of a pulse rate of sodium iodide and cesium iodide pulse rate. It has an energy band of 20 to 250 keV, effective area of roughly 5,000 centimeters square. And located on the other side of this platform is a medium energy telescope. It's somehow made of a silicon detector. Bandwidth is from 5 to 30 keV, 1,000 centimeters square of effective area. Other side of this platform is a low energy telescope. It's kind of CCD detector, and bandwidth is somehow of 1 to 15 keV. Effective area is not that large, but still have a few hundred centimeters square. And here, the figure just show you the effective area that's covered by these three telescopes within a bandwidth of from 1 to up to a few hundred keV. And if you take a look at this table, you will get some feeling at how this mission is compare for the properties of, for example, energy band detection area and energy and time solutions. The comparable, if it's compared to some other missions like previous RSGE and the current integral SwiftBat or even NewStar, you have a feeling that we have the largest energy coverage, and we have a largest effective area, the hard X-rays. Although the soft X-rays, the effective area is not that large, but it's first time for us to use a CCD detector to observe very bright sources and without any kind of a very strong power problem. And all these three telescopes were designed to work in a collimated way, and in that case, we have most of these detectors be designed with smaller field view, as shown in this table. But some of these detectors are designed with larger field view, just in order to detect the diffuse emission background. And also, even some of the detector was set to be blunt to measure the particle background. And for orientation of this small field view detector, it was divided into three groups. For each every two groups, the orientation is shifted by 60 degrees, just in order to have a better modulations once you perform scan observations. So that we can use the image method developed by the former PI. I will show you this later. For the observing mode, that we have a pointed observation of observing mode, for which typical duration could be one orbit to up to a few tens of days. For small area scanning mode, and depending on the scanning parameters, we'll have, for example, a typical duration of a few hours up to a few days. And it can be used to perform the Galactic plan survey. And also GRB mode, I will come back to this issue again later. In 2016, we released to the domestic scientists of China to call for the first AO for the proposals. Finally, we selected totally 90 proposals for which the majority of the solicited source observations is about XRB, which occupied roughly 50% of the entire sources. And for each proposal, it has to go through a series of procedures for evaluations. One is somehow technical evaluations, and another one is scientific evaluations. Finally, we have different type of these proposals and different grade. And for the normal proposals, the solicited exposure could be over the 300 days. And also for TOO, we need even 1,000 days or even more. So these proposals constitute the core science program of HXMT, and also correspondingly the core science team for the mission. And for the observations, it has to be subject to a series of constraints. One is that somehow the solar avoidance angle, we have to also take into account this Earth collisions and SAA, and also even moon avoidance angle. So finally, we have a total efficiency of roughly 50% for pointed observations. And we have good, relatively quick response to TOO observations. So that means once we have the trigger, either from international societies or from ourselves, we can go through a series of procedures. And finally, we can perform the TOO observations within 5 hours. As one example is shown in here is for this double neutron star merger event. We got trigger at 9:30 in the midnight, and we performed the observations within 5 hours. For the performed observations, as shown in this table, that we have done quite a lot so far in the last year, and it can be we observed source of different types, for example, supernova remnant pulsars, XRB of either black hole neutron star systems, and also actual galactic sources, blank skies, and galactic plan survey, and so on and so forth. And here shows the source name, and this column shows the pointed numbers, and this column shows so far the accumulated exposure for each source observed so far by us. And the figure shows how this outsky is covered so far by this mission, and in an equatorial frame. Here is a green belt, just shows how this galactic plan is scanned by us, and this yellow belt shows the test of this outsky survey mode, and this red point just show you the pointed observations for individual bright sources. Blue lines show the slew of the mission, the telescope between every two observations. For the preliminary result, firstly, let's take a look at how a galactic plan was scanned by us. For the entire galactic plane, we subdivided into 22 patches, each with a size of 20 by 20 degree. And here, there's a small movie to show you how this single scan will be performed and how this entire galactic plane will be scanned patch by patch until the entire galactic plane is fully covered by us. And also, nextly, I will show you how the galactic plane will be observed by us in the scanning mode in the first year. It's somehow expected exposure, but in reality, so far till the end of March, all the galactic plane is scanned in this. The exposure is look like this. And once we have the scanned data, in principle, we have two ways to handle it. One is that we just feed the background light curve together with the instrumental response to the point sources are shown in here, and the small spikes, which is somewhat triangle, to represent the point source. And put together this part and then feed the light curve, and then we can know the position and the flux of the source within the field of view. Alternatively, we can also use the so-called directed modulation method, which was developed by the former PI, Professor Li, which can be used to transform this scanned light curve from one-dimensional to two-dimensional image. So that in that case, we can get information of source position and also flux. As one example is that I show here for scan light curve, we can detect, for example, this one is PW source with detection significance of roughly a sigma, which is not included by Maxi catalog, just because we have better sensitivity. And we have also the chance to detect a new source. Here shows one example of a new source candidate, which is somehow shows up in the scanning light curve with a flux of roughly 7 millicurie with a significance of roughly 7 sigma. And of course, we have a lot of data in the scanning of galactic plane, and we can use it to monitor a lot of sources for their flux variabilities on long time scales. As shown in the one example is this newly discovered neutron star high-mass X-ray binary systems in their outburst. It can be well monitored by us with a systematic flux error of roughly 1%, which can be determined by observing the curve over a long time period. Of course, our major advantage is a very large effective area, the hard X-rays. Then we can use it to observe the so-called cyclotron absorption lines, which is somehow our advantage. The point is that, according to this formula, the centroid of this absorption lines not only depend on the local magnetic field on the surface of neutron star, but also depend on the theta angle. The theta angle is defined as the instant direction of the photon with respect to the local magnetic field. And once we have this hot spot, which is rotating along the spin axis of a neutron star, then according to this figure, the cross-section of these absorption lines and as well the centroid energy will changing along against the different, this theta angle. So that gives us a chance to disentangle in the spin possible fields or spin light curve with all the kind of effect. And also, we did observe quite a few sources with absorption lines. One interesting example is this GR0108. It was detected by us with very high significance of absorption line signal with only roughly 200 kilosecond. But before that, as shown in here, is tentatively observed at roughly 5 or 4 sigma by the previous observation of Neutron and Suzaku. To give us the indication that the absorption lines are located at roughly 80 keV, which shows that it could be one of the most highest magnetic field so far we detected directly in the universe from a surface of neutron star. Of course, the outburst from either black hole or neutron star system is our first priority for observations. One example is a newly discovered high-mass actually binary neutron star systems. And shown here is Barrett light curve. So if Barrett light curve give us a feeling that the top flux of the outburst can reach to up to a few crab, and quite bright. And for spin light curve, for spin frequency of the neutron star, it's highly modulated by the orbital movement, which is somehow Doppler effect give influence on spin frequency. And another effect is somehow the accreting matter created on the surface of neutron star, it will spin up the neutron star and give another modulation on the spin frequency. So only you have take into account properly of these two effects, you have a reasonable spin frequency evolution against the time, as shown here, the residual of the change of this spin frequency. Similar exercise can also be performed by using our data. You see here, residual is quite reasonable. And of course, we have a lot of data we can monitor in details for how this spin pulse profile is evolving in different time scale, even a long time scale or short time scale at a very broad energy band. And this is another example. So it's an outburst of so-called Maxi source. It was detected in last September by Maxi and Swift. It's a kind of a black hole candidate. And as shown here, the Maxi light curve at soft X-ray, say somehow the top flux can again be around a few crab, quite bright. And from beginning to top flux is time period we accumulated roughly over the 100 kilosecond. And we can use that amount of data to perform the timing analysis in details. For example, we detect the so-called type C QPO, which is somehow typical to the intermediate hard state of a black hole outburst in all three telescopes in three energy band with roughly a few kiloseconds. And most interestingly, is if you look into the details of how the properties of QPO in aspect of either frequency or RMS, you will have the we have for the first time to know the properties of this QPO at energies above a few tens of keV up to even 100 keV, as shown here, and it's the first time you can do it. And because we have for our low energy detectors, somehow we are free of this power up problem, and we have a very large factor area at the hard X-rays. We can use it to observe the thermonuclear burning event occurred on the surface of neutron star. One example is here is a PRE burst. It's a kind of a photospheric radius expansion event. And by observing that event, we got at hard X-rays, in the rising part of this light curve, we detected additional HE burst. And shown it here quite prominently. Here we have 5 sigma of detections. If you look into the details of this data point and in the spectral fitting, you will see that at hard X-rays, there is somehow a very strong exercise in hard X-rays. And so the last part of this talk, I will address a little bit on how GRB will be observed by us. Just before the launch, and the original design of GRB observations is just we want to use it to perform afterglow observations by using the LE detector at soft X-rays by performing the either pointed observations or scanning. But just around launching time, the PI, Professor Zhuang, he decided to extend these capabilities by using the cesium iodide detector of HE to perform the prompt emission detections. The principle is that we know that photons can come towards this platform or detector from all directions. If the photon with a lower energies, it will, the collimator will take functions to block to constrain that we can only observe the photons from within the field view. But if the photon energy is high enough, it can penetrate the local structures of either the collimator or the platform. It can be recorded by cesium iodide. So in that way, as a result, we have two working mode for observing GRB. One is a regular mode, and another is a GRB mode. For the regular mode, we just have the normal high voltage of this PMT of HE, but for this GRB mode, we lower the high voltage of PMT, for example, by 50%. In that case, we can promote the working energy band of either cesium iodide or solid iodine to up to a few MeV, from a few hundred keV to a few MeV. So in that case, we got a good position in observing or detecting this so-called GRB peak, which is predicted by different models. For the peak, just located from different model predictions around the energy band of a few hundred keV or even higher. And we decided also to spend a lot of time in GRB mode. And this figure shows how this cesium iodide, once you have GRB mode, you have from different incident angle of these photons, you will have different effective area. But on average, we will have roughly 1,000 centimeters square at hard X-ray up to a few MeV energy band, which turned out to be the largest one so far. And of course, if you regard the local structures of a platform as a kind of a coordinate mask, and you can use it to know a little bit for the incident direction of GRB. This shows the simulations on the different directions of incident photons, and how this response of cesium iodide will give us the response to that directions. And in that way, we can localize the GRB incident direction to a position of as good as a few degrees. Of course, we have a large effective area. We can abundant of photons, and we can use it to perform the tiny timing analysis once you have a light curve GRB. And shown here two examples. You have a very bright GRBs, and you can look into the tiny structures of the in light curve. Of course, the power of this mission is that we can use it to observe the short and hard GRB, so-called the short GRB. And as one example is that for this GRB, our detection significance is is roughly 12. It's much better than from GBM and even SPI ACS as shown here. Of course, we join as well the IPN, the joint interplanetary network, just to localize the GRB directions, incident directions, according to the different arriving time because of the distance of a different detector. We also can do it. For GWM observations, we contribute also quite a lot. We monitored at least 6 GW triggers for this famous double neutron star merger event. We observe it, but we have not positive detections just because this is not a normal short GRB. It turned out to be very soft in spectrum. We put very strong constraint in the hard X-rays, in the tailed soft gamma rays on the flux limit. And we joined MAMA paper, and we published the result independently in Chinese journal. And shown here, I showed before that we have a quick response so that we can observe this event in early time. And we were also among the only 4 gamma ray and X-ray telescopes which can monitor the entire period of this event. So finally, it turned out that we were listed in the 7th collaborators in these very large papers. Here shows the details for these stories, that in that time period, the entire sky, including the position with this neutron star merger positions, were always visible by us. The only problem for us is somehow these blue regions, which represent the Earth's occultation at that time period. So in that way, we have light curve and hard X-rays for localize this. It include not only the GW trigger, but also the GRB trigger and before and afterward. So in that case, we can publish the upper limit for the precursor time period and trigger time period as somehow the extended time period for this famous neutron star merger event. So finally, I will spend show you two slides, which is somehow taken from our collaborators of Ferrara universities, led by Professor Filippo Frontero, and their group performed very good joint researches on our core sciences for GRB, and also these two slides were taken from the talk of Cristiano, which presented on the parallel session in the code of MG3, just focus on the current progresses of his Chinese mission. And the story is that once you consider joint missions to put together all of our high-G detector with somehow at low energies of BAT and GBM, you'll have very promising prospects of GRB observations in future, which can be used to, as shown by these nice simulations done by Cristiano, that we can measure the peak quite well, yeah. Especially for short GRB, it has a very hard and hard spectrum, but faint source, and then you definitely need a large effective area to constrain the E-peak, which is supposed to be larger than the long GRB. And we can do even better and to perform the time lag for these hard X-rays with respect to the lower energies, because if you have joint mission, you can, in principle, you can do it. And of course, this time lag will allow us to investigate if this time lag is due to the intrinsic, the emission region differences, or just in jet scenarios, just kind of a Doppler effect, somehow geometry effect. So the power of this joint mission lies in that we could have a E-peak, and we could have a time lag, and we could also have this spectral variations along with the burst, and also E-peak and time lag evolution of along with the burst. So we can do quite a lot. And so finally, I'll give the summary. Insight-HXMT is China's first X-ray astronomy satellite, and it covers quite a wide energy band, including soft X-rays and also the hard X-rays, even at the soft gamma rays in all sky mode. And so far, it finished successfully its performance verification phase by the end of last year, and also the in-orbit calibrations has been done more or less and almost finished at this moment. And the Galactic plan is well scanned by us, and we spend a lot of time on that. And many bright sources were observed by us by using pointed observations. Could be either black hole or neutron star X-ray binary systems. And also we executed a lot of TOO observations, and roughly 100 GRB detected by us so far. And of course, the international collaborations are very welcome to. It can be done in principle in 3 ways. One is that before launch, we have quite a few partners give us a lot of contributions for this payload and for this mission. And that partner became collaborators of us automatically. And the second way is that you can, if you have resources of either in space or on ground for multi-wavelength observations, you can join us, and we can enjoy the scientific output by coordinate the multi-wavelength observations. Of course, if you have a very strong background, if you have some idea, you can just go directly to the web page of this mission and download and fill in a few simple form, and you'll get approved by the PI, and you'll become part of us. Then we can enjoy the entire mission. That's all for the talk. Thanks for your attention.
Thank you so much. Okay, my question was, there is a very successful American device now on the space station. It's nicer.
Oh, nicer, yeah.
56, you know.
Yeah.
Yes, do you plan to collaborate to make, because they have much better response in the standard and soft X-rays, and
Yeah.
you, at the same time, they do not have at all medium energy and hard X-rays.
Yeah, this is a very good comment because NICER is somehow extremely good detectors at soft X-rays. And meanwhile, it is also more or less free of this power-up problem. But the energy band is quite soft. It is generally, I think it is below 8 keV or even lower. So I think if you put together these two missions, it will be extremely good for us. And we'd like to do that in the near future if we have the chance to collaborate with them. Of course, it's a very good comment.
What is the lifetime of your mission?
I showed before it's at least 4 years. We hope
4
it can be the longer the better. Yeah.
I just returned from Moscow and I have seen the spacecraft Spectrum X, you know it, with Erosita and Arctic Sea, which are planned to fly next year in March. And we will be scanning the sky. And we'll be very glad to inform you if there will be something bright which you can observe.
Yeah, it will be a good trigger for us. And also in China, we will also launch a so-called Einstein probe, the EP. It will be the most sensitive Oscar monitor, even flow. Yeah, it is somehow.
What is the launch date?
It's somehow, I think, it's over than 2020, or I cannot recall it quite correctly, but it was fully supported and got the money and just waiting for the launch date. Yeah.
2020.
Beyond 2020, I cannot give you an exact number because I'm not involved into that team.
Okay, thank you.
Yeah, thanks a lot.
Just one question, Raymond.
Of course, we are very interested in GRB MEV radiation. How soon we will have data on GRB and if they will be made public?
Yeah, you mean our mission? The GRB issue is quite promising and it's a prospect. It's a very good prospect, but we are currently be faced with the in-orbit calibrations. You need, for example, if you want to measure the e-peak, you need to calibrate your energy response of a detector quite well. And before we can finish that, it will be difficult for us to measure jointly this e-peak with other missions. It's a big task for us. So the current method is we are currently considering is that once the simulations, but that turned out to be not enough. And we are currently using, for example, another two ways. One is that to use the simultaneous GRB observations together with other missions as the input of spectral parameters to know how good is our instrumental response. So another way is that we just use crop. We use crop. We know that crop is position, and we can use it as the instrumental response calibrations. The difficulty is that we have to calibrate all directions. The different instant directions of GRB will have a slightly different response of the instrument. That makes big trouble for us. So the strategy is that we think that might be once we detect GRB jointly with some other missions, we can afterward put the crop in that directions of that GRB directions to make the follow-up calibrations just specific to that directions, which in principle can take a few hundred kiloseconds to know the instrumental response.
So you rely on the other one, at least in this time.
Yeah, for the crop we only we do not need because we know the crop spectrum. Only for GRB we depend on the other missions. Yeah.
Okay, we thanks again the speakers. Now it's time for the coffee break. And we should reconvene here in 20 minutes.